Hello everyone, my name is Ken and I will be guiding you through understanding topological sort today. We'll be covering its definition and implementation, starting from a high-level intuition, then walk through an example while diving into the code. So let's try to understand why do we need topological sort. Well, imagine if you're planning your semester, you have to clear all the prerequisites before enrolling in an advanced course. Topological sort help you to determine the order for course selection so that you can fulfill the requirement. Well, similarly, in software development, the build system use topological sort to determine the order for file compilation. Let's look at the definition here. Topological sort is an algorithm that orders the vertices of a directed acyclic graph linearly, so that for every directed edge u to v, U comes before V in the result sequence. Let's look at the example here. The sorted result would be 0, 1, 2, noticing that 0 comes before 1 because there's an edge from 0 going to node 1, and 1 placed before 2 because there's an edge from 1 going to 2. So here comes the question. How does the topological sort knows which node to go to the result array next? Think about it closely. Are they actually looking for a node with 0 incoming edges? Well, we would definitely need to start from a node with no incoming edges. That's the intuition here. Knowing a node that has no incoming edges, meaning that that node has no prerequisite, and we are free to add it into the result, which is very nice. So what we do next is to remove that node from the graph and then update its neighbors in degree. 1 becomes 0 and 2 becomes 1. And we do this again. We look for the nodes that has 0 incoming degrees, remove it from the graph, and then update its neighbors in degree. We do it again, remove that node with 0 in degrees, and we're done. Noticing that the removal order is actually the topological sorting result. Great! Now we know the logic for topological sorting. We can look at the code now. The code here starts on the line 9, where we have a result array, a queue for breadth first search, and an in degree mapping which we will fill in right now. So looking for the code here, line 3, we go through all the nodes, and then for the neighbors of that node, we increment the in degree of that neighbor by 1. So here we have neighbor 1, we increment it. We have neighbor 2, we increment 2's in degree. And also we have a 2 again, we increment 2's in degree again, and finishing here. And then we're back to line 13, where we have to go through the nodes in a in degree mapping. Whenever the node has an in degree of 0, we add it to the queue. So obviously here we only have node 0 with an in degree of 0. We'll add it to the queue. 0. Now here comes the BFS in this while loop. We'll go through the code first. The first thing they do is to pop it from the queue and then add it to the resulting array. Then for the popped node, we look for its neighbor and check if its neighbor's in degree, well, not checking, but decrement the neighbors in degree by 1. This is the update step, and if the updated neighbors in degree becomes 0, we add it to the queue. So let me show you how this takes place here. We pop the queue and add it to the result array. So for this popped item 0, we look for its neighbor 1 and 2. We update its in degree, noticing that 1 in degree for node 1 becomes 0, so we add it to the queue. Finishing the first iteration of this while loop, we do it again. Pop 1 add 1 into the result array, and then look for its neighbor, 2, and we update 2's in degree. Now 2 becomes 0, 2's in degree becomes 0, so we add 2 into the queue. This is the end of the second iteration. For the third iteration, we pop 2 from the queue and insert it into the result array and look for its neighbor. Since 2 doesn't have any neighbors, so it's the end of this algorithm. So that's it. Thank you for joining. If you have any question, please let me know.